Okay, we're going to get started here, so if you're coming in, please take a seat. Great. Okay, good morning, everyone. So nice to see you all here. I have the pleasure of chairing this morning's session. I'm very excited to hear about all of the talks. We're going to kick the session off with the first two will be virtual talks, and the very first session will be will be from Olivier Bernet, who's going to talk to us about molecular photoevaporation flow from a young protoplanetary disk. So the floor is yours, Olivier.
Thank you very much, and thanks to all the organizers, especially for providing the opportunity to have these virtual talks. This is really, really great. So my name is Olivier Bernet, and I'm going to present you some of the results of the PDRs for All program. Let's see. Here we go. So the PDRs for All program is an ERS, Early Release Science program, and it's dedicated to the study of photodissociation regions. The photodissociation regions are the interfaces between at the surface of molecular clouds, where most of the UV radiation from massive stars in galaxies is absorbed. And this energy is re-emitted in the infrared. And in fact, most of the emission you see in the infrared spectra observed by JWST of nearby and distant galaxy arises from these photodissociation regions. So the PDRs for All Early Release Science team is the largest ERS team, in fact. So we have a PI team which is composed of Els Peters, Emilia Barr, and myself. Then we have this large extended core team of about 40 people. And here those who are highlighted are the people from the data reduction team, which have worked a lot in the recent weeks, including to provide some of the results that I'm going to show to you today. So we also have over 120 science collaborators from 18 different countries. And the target we observed is the Orion bar photodissociation region. We had a total time of 40 hours, which is split in these three instruments. And here, MIRI is in red because we still haven't observed with the integral field unit in spectroscopy. And this data should arrive early in 2023. So on September 10, 2022, we obtained this image of the inner Orion Nebula with NIRCam, and you can see numerous young stellar objects in this image of various sizes inside their cocoons, and these young stars have various masses. And the most massive stars are the trapezium cluster stars, which are not inside the field of view, but just next to it here on the upper right corner. And we did that in purpose to avoid the saturation of the NIRCam instrument. So this dark lane that you see here in the image is the Orion bar, and we can zoom in into this bar. So this is really the core of the photodissociation region. So the gas basically goes to fully ionized gas at 10 to the 4 K to fully molecular hydrogen gas at a temperature of about 30 K. And this happens over small scales of about 0.1 parsec. So across this interface, we obtained a NearSpec Mosaic. And these are three template spectra that we extracted from this Mosaic. And you can see that these are extremely rich NearSpec spectra. There are forests of lines. Most of these lines are coming from either molecular hydrogen or hydrogen recombination lines. You can also recognize these bands here, which are attributed to the emission of polycyclic aromatic molecules, which were already mentioned in this conference. And there are a number of other species that are also present in these spectra. So we currently have 3 papers in preparation to describe these early results. One by Els Peters, which is dedicated to this spectroscopic data of the Orion bar. One paper by Emilia Barr, who is looking really at the imaging of the inner Orion Nebula. And one which is dedicated to a peculiar object which we observed in our field of view, and which is this object that you have here in the Orion bar. So what you see here is a 3-color NIRCam image And what is physically present is that you have a protoplanetary disk here that is seen edge on. That's the dark lane of the protoplanetary disk. And this disk is enshrouded inside an envelope of molecular hydrogen that is bright here in red in the 212 filter of NIRCam. And then in blue, you have this feature here, which is a jet emanating from the central star inside this protoplanetary disk. So we have a nice image gallery, which goes from Hubble through JWST into ALMA over the wavelength range. You see the disk here in absorption against the bright background of the Orion bar at all visible and near-infrared wavelengths up to the 3.3 micron filter here. And if you go to the millimeter wavelengths with ALMA, you will see the dust emission and also the emission from the cold molecular gas inside this protoplanetary disk. What is striking is the presence of this envelope of warm molecular gas that is detected in H2, in the PAH filter with NIRCam as well, and in HCO+ with ALMA. So if I go back to this image, the current picture that we have for this object currently is the following. So you have this edge-on protoplanetary disk, which is illuminated by the far ultraviolet photons of the trapezium cluster. And this radiation hits the protoplanetary disk and heats up the disk. And because of the increase of the local pressure, this results in the ejection of gas from the surface of the protoplanetary disk. And this gas is feeding the envelope that is surrounding this protoplanetary disk. So what we think we see is a photoevaporation flow. And these photoevaporation flows are extremely important because it is believed that this mechanism of photoevaporation is one of the main mechanisms for protoplanetary disks to lose mass. And hence, this mechanism puts a limit on the time scale for the formation of planets in protoplanetary disks. So this is really the first time that with JWST and ALMA combined, we can look in details at such a photoevaporation flow. So ALMA is extremely useful in combination to JWST because it provides the kinematics, and what you see here is a position velocity diagram across the disk plane obtained with the ALMA HCO+ emission. And basically what you see is the rotation of the disk, and you can overplot on this PV diagram these curves, which are the Keplerian contours. And you can use that to determine the mass of the central star. And when you do that, what you find is that the mass of the central star is typically 0.1 solar mass. It can be a little bit more, but really it's a low mass star that you have inside this protoplanetary disk. We cannot see the star, but yet with these kinematics, we can determine its mass. So you can also use the results from 3D models of a photoevaporating protoplanetary disk. And make the synthetic PV diagram of these models, and this can guide you to understand what you see in the observations. And one key signature here is the presence of emission of HCO+ in this region of the diagram, which are non-Keplerian motions, so motions which are associated with gas that is not in Keplerian rotation with the disk. And in this case, this is a signature of the photoevaporation, and we believe that we also see this non-Keplerian motion here in the observations. And that's also a sign in the kinematical space of this photoevaporation flow. Okay, so what ALMA doesn't give you, and what is also key, is the physical properties of the gas in this photoevaporation flow, in particular the density and the temperature. And to extract these physical properties, you can use the NearSpec data. So this is the NearSpec spectrum of the 203506 system. And you can see that this is an extremely rich spectrum. Most of the lines you see here are molecular hydrogen and H recombination lines. You see also the emission from the polycyclic aromatic hydrocarbons. And here, this comb of lines that you see is not noise, it's the emission of the CO molecule that is present also in this envelope. So we can zoom in some specific regions of the spectrum to see it in more details. In this 3 micron range here, we have clearly detected the OH molecule in emission. Here, as I said, we see the emission from CO and perhaps 13CO. We also see the absorption of the CO2 ice present in the protoplanetary disk. Here, near 4 microns, we have detected the CH plus molecule in emission. And if you look at this part of the spectrum, above these features which are attributed to pH molecules, you see these narrow lines, which we think are molecules, but we still haven't identified what these species are in this object. Okay, so you can use the data, the lines from the NearSpec spectrum, and in particular the H2 lines. You can extract the fluxes from these lines, and you can use that to constrain PDR models like the Methane PDR code. And you can use a grid of model and try and find what is the best model that you get for the observed H2 lines. So here we use 29 H2 lines observed with NearSpec. And so this is the chi-square space. And the best model that we get from this analysis is a model in which we have a density of 3 times 10 to the 5 per cubic centimeter and a temperature of about 800 K. We can also use radiative transfer models to fit the emissions from the molecules we have detected. And all these models point to gas temperatures for this photoevaporation flow for this molecular envelope of about 800 K, in good agreement with the temperature we derive from the PDR model. And so these numbers are extremely useful because from them we can derive the mass loss rate. And so this is really one of the first times that we can directly assess the mass loss rate from a protoplanetary disk. And we find this number, so we have relatively conservative numbers here due to the methodological uncertainties, but it's in this range of 3 to 30 times 10 to the minus 8 solar masses per year. So the last thing we can do is use the NearCam data to extract the abundance of the pH molecules inside the flow. And when we do that, we get an abundance which is characterized by this number, which may not mean a lot to you, but that you just have to remember that it's a large abundance, and that results in a high UV absorption cross-section inside the photoevaporation flow because pH molecule absorb UV light very efficiently. So we can sort of now rationalize things around these theoretical predictions, which shows the mass loss rate of a protoplanetary disk for the 203-506 system, so theoretical prediction, as a function of the absorption cross-section in the UV, and we can put the observational constraints now, and you find that these constraints put you in a range of relatively low mass loss rates and relatively high UV absorption cross-sections, which fit well together with the theoretical predictions. So the conclusions about this study is that we detected a molecular envelope around the protoplanetary disk combining JWST and ALMA. We have a very rich NearSpec spectrum with a lot of molecular lines and a lot of molecular gas that is not in Keplerian motion. So this is suggestive of a photoevaporation flow that we can characterize. In particular, it has a large abundance of pHs, and this large abundance, in fact, of PAS protects the protoplanetary disk from the UV radiation of the massive stars, and so in a way, it allows to keep the mass loss rates relatively low. So if you want to sum up, a way to say it is that planet formation near massive stars, in this case, can be protected by the presence of these pH molecules in the envelope surrounding this protoplanetary disk. But clearly, we need to observe more of these systems in different phases of evolution, different ages, and also different radiation fields. And I want to insist on the unique synergy between JWST and ALMA for this kind of studies. So a little bit of advertisement. We have these 3 papers in preparation, and on our website there is a lot of information that you can access to. In particular, we have the webinars, and our next webinar will be next next Friday, but all the other ones are recorded and you can find them on our website. And that's it for me. Thanks.
Wow, thank you so much. Do we have any questions? Do we have any online? Susan, can you?
Great, thanks. Really wonderful to see. Nancy Levinson from the Space Telescope. I was wondering, in the example that you showed, the reason for the asymmetry with a bright spot on just one side, is it just happenstance of the pre-existing conditions or some foreground background issue or something else?
Yes, in fact, that's something we are trying to solve. And it's not clear whether it's linked to the presence of the UV photons from the massive stars, or if it's due to the interaction of the jet with the envelope, or a combination of both. So this is something that we will investigate in more details in the future. In particular, also trying to use irradiated shock models to reproduce our near-spec observations.
Great. Any more questions? Yep, one here.
Thank you for the nice talk. This is Jonathan Tan, Chalmers, University of Virginia. You showed constraints on the PAH content in the photoevaporation flow. Do you have constraints on the more generally on the dust content in the flow? I assume dust is in your PDR model, but is it playing a role in setting the temperature or other aspects?
So it's very hard to have for the moment to have the constraints on the dust. We have the ALMA data which provide constraints on the dust properties in the disk, but in the envelope we do not see any signs of dust emission for the moment, nor signs of dust absorption. But we may be just limited by the sensitivity. So it's something which is extremely difficult to constrain for the moment. But perhaps this is something that we should look into with the MIRI data, for instance, where we may have a little bit of emission from dust at thermal equilibrium.
I'm going to take one question from online. Yep.
Yeah, so there is one question by Mario Warcello. Does the shield, sorry? Yeah, I think it's on. Does the shielding by pH changes when photoevaporation is driven by extreme ultraviolet photons very close to massive stars?
That's an extremely good question. I don't have the answer to that because we haven't been able so far to look at the emission from PAHs or the absence of emission of PAHs from in these kind of systems. What we know is that so there is another photoevaporating protoplanetary disk in Orion, which is closer to the trapezium cluster, in which we were able in the past from the ground to measure the abundance of PAHs, and there the abundance is much lower. So it's possible that if you go very close to the trapezium cluster, you will have even less PAHs, and so they cannot really protect you anymore.
Great, thank you. Let's thank Olivia again. And I'm going to ask Julia Perotti, who should be online, to share your screen, please.
Right, can you see my screen and hear me well?
Cannot see your screen yet. Are you sharing? Oh, there we go. We can see it now, and we can hear you well. So next up we have Julia Perotti, who's going to speak to us about PDS 70. Thank you. The floor is yours.
All right, so what a great pleasure to join this conference. Thank you very much for the organizer, and to present you some of the really first results of the MIRI mid-infrared disk survey, or MINDS. This is a GTO program led by Thomas Henning that has been using the MIRI instrument, the medium resolution spectroscopy mode, and will be using this instrument, but not only, also NearSpec and NearCam, to observe 50 disks around T-Tauri stars, 2 disks around more massive stars, 10 faint disks around brown dwarfs, and 5 young gas-rich debris disks. The GTO program is part of the MIRI European Consortium, which is a collaboration of 10 European countries that were involved in designing, manufacturing, and commissioning MIRI. As far as it concerns the DISC program, the MINDS survey, the main goal is to study the innermost regions of protoplanetary disks and debris disks where terrestrial planets form. I would like to take a step back, set the stage for these James Webb results in order to let you understand what do we gain when studying disks in the mid-infrared and what we learned by looking at disks with Spitzer IRS. So as you can see from this beautiful cartoon from Anna Miotello, the PP7 chapter, when we are probing, when we are studying disks in the mid-infrared, we are targeting radii below 10 AU, the upper disk surface layers, and well, the mid-plane for nearby adjunct disks. Here in these regions, the temperatures are high enough for key molecular tracers of planet formation to strongly emit. So you can see here in this slab model that there are plenty of water lines, forest of water lines. Hydrogen cyanide is also present, which is a key molecule in the start of the chemistry leading to the RNA world. And at the same time, in this spectrum range covered by MIRI, we can observe symmetric molecules such as CO2 and, well, acetylene, C2H2, which are not accessible with ALMA because they don't have a permanent dipole moment. Right, so right now we're entering the stage where we can finally combine the information ALMA has provided of the outer disk regions and the chemical processes and physical processes there, together with the chemical inventory, when the innermost regions that we are now looking at for the first time at high resolution with Webb. Right, from Spitzer RS, we learned that the simple organics that I've just listed are present in the terrestrial planet forming zone. Here I'm showing the beautiful press release spectra from Carr and Najita 2008 and Salik et al. 2011 that shows that water, hydrogen cyanide, acetylene, carbon dioxide are present. But let's now move on. I would like to give you a glimpse of some of the first MINDS results. I would like to start out with this spectrum of a T-Tor disk. This is a project led by Sierra Grant. You can see, again, as we saw already before in the previous talk, a forest of lines that Webb, the MIRI, and the MRS instrument is able to detect. This source was showing a particularly strong CO2 emission here, which was previously detected with Spitzer, and also acetylene was previously detected. But right now, with the much higher resolution of MIRI, we're also able to detect hydrogen cyanide, several water lines, as well as 13 CO2. So this is the first time that isotopology of CO2 is detected in a protoplanetary disk. Stay tuned for this result, which will be submitted very soon. This is another disk, another exciting result. This is a spectrum of a disk around a very low mass star. This is a work carried out by Aditya Arabi et al. And well, you can see that here again we are detecting 13 CO2, the optically thin tracer of CO2, as well as HC3N and a really bright emission of benzene. So this is the first time that we are detecting benzene in a protoplanetary disk, and in particular that we are accessing the regions of disks around low mass stars, which are really challenging to access with ALMA. This first result is a project led by Giulio Bettoni and Bernard Tabon. This is an incredible spectrum. We have never, which is really unusual. We've never seen such a spectral profile before. And well, this is for a number of reasons. First of all, we are not identifying silicate emission, neither at 10 nor at 18 microns here. And we are not detecting water lines or OH lines here, but instead several hydrogen recombination line, molecular hydrogen lines, and you can clearly see these two really prominent bands, these broad bands here and here around 13.7 microns, which are attributed to acetylene. Besides acetylene, we're also detecting benzene also in this target, hydrogen cyanide, C4H2, as well as the isotopologue of acetylene. So this indicates that, together with the spectrum I just showed you before, the inner disk, the inner regions of protoplanetary disks around very low mass star are really extremely carbon rich. And this indicates the oxygen must be locked up in non-migrating pebbles that are locating outside the water ice line. The carbon to oxygen ratio in these regions is greater than 1, which is a significant indication for the planets, for the composition of the planets that might be formed around these very low mass objects. For the remainder of this talk, I would like to focus on PDS-70, which is the system I worked most over the last months. And well, this is a unique system because this is the only system where 2 accreting giant protoplanets have been directly imaged, PDS-70C and PDS-70B here. These 2 giant planets are carving this large gap here that separates the outer disk with an inner disk, which extends to 9 AU. So with ALMA, we're not able to access this inner disk, but now we are with spectroscopy. So the system has been studied in detail in the near-infrared, VLT, SPHERE, and SYMPHONY data that had allowed to detect planet PDS-70B and C. And when ALMA has been characterizing the outer disk structure, just last year, a circumplanetary disk has been detected towards planet PDS-70C. And while ALMA has been transformative in studying the chemistry in this system too, and well, these 2 giant protoplanets seems to be accreting from material that has a carbon to oxygen ratio greater than 1. Therefore, we would expect the inner disk material to be oxygen poor. In this talk, I will populate, well, until now we've been missing an important hexagon in the study of the system, and namely the study of PDS-70 in the mid-infrared at high resolution. And well, in this talk, I will populate this hexagon, but not with a pretty picture, instead with a spectrum. And well, this is great because if a picture is worth 1,000 words, then a spectrum gives us more information because each transition tells us about the physical processes occurring in this system. So this is the first James Webb Ramirez spectrum of the PDS-70 system, the full spectrum from 4.9 up to 27 microns. And these are really exciting results, a beautiful data set where, first of all, we are seeing a really prominent silicate emission around 10 micron. And well, this indicates that the inner disk atmosphere is reached by small submicron dust grains populating the inner disk. And if we look closely to the spectrum, we can see a number of crystalline dust features. For instance, phosphorite here at 11 microns, again at 16 microns, and also longer wavelengths between 20 and 23 microns. So this indicates that the grains, dust grains in this system have been thermally processed. Right, if we compare the James Webb MIRI spectrum with a Spitzer low resolution spectrum that was taken about 15 years ago, then we find a really large flux offset along their wavelengths. And so this discrepancy, it's about a factor of 1.5, is too large to be attributed to changes in the background thermal emission. And so this is time variability, probably due to a change of the inner disk geometry, and in particular due to inner warps created by planets in the system that are increasing the size of the inner disk edge, therefore shadowing the outer disk, which results then in this offset. It is not it. If we zoom in, and well, I promise this is not noise, we can detect gas emission lines, so we can really grasp what MIRI MRS is capable of. And if we're zooming in even further and compare these lines with these lab models, then we can identify ortho and para vibrational lines in the 7-micron region, which is a great result because it's the first time that we're detecting water vapor in a disk that we know that is hosting 2 accreting protoplanets. So the excitation temperature of the water, so this is very much of a work in progress, is around 500, 600 Kelvin for an emitting radius of about 0.1, 0.2. And well, besides water, we are detecting also molecular hydrogen line, the S5 line, around 6.9. With Spitzer RS low resolution data, we will not been able to detect water at all, as you can see here in this comparison, in this zoom in. And well, this brings me back to a prediction that dates back to 2010 by Klaus Pontoppidan, where here you can see the James Webb MIRI prediction of how spectrum will look like. And well, right now we can see that Klaus was right because we are able to resolve water complexes and even especially resolve lines in some cases in the MIRI range. So the fact that we are detecting water in the inner disk of the PDS-70 system means that the planet-induced gap here, the gap that has been carved by the 2 accreting protoplanets, has not completely drained the inner disk of oxygen. And therefore, planets that might be forming in the inner disk do not start as dry as we thought. But a lot more has to come. This is just the beginning. Near Spec and near Cam observations will be taken and will be extremely complementary with the MIRI data that I've showed you now. So stay tuned for new data coming up in 2023 for this system. And well, this brings me to my final slide. I would like you to remember from this talk about the MINDS survey, the MIRI mid-infrared disk survey. We have already witnessed what James Webb is capable of in allowing us to understand what is the composition in the inner disk regions, in the innermost AU of protoplanetary disks. When it comes to disks around very low mass stars, we are seeing that they are significantly carbon rich. And well, I've been showing you the NearInfrared spectrum of the PDS-70 system, shows time variability, and we are detecting water vapor, indicating that the inner disk is not completely drained of oxygen due to the presence of, in spite of the presence of the large gap. And with that, I would like to thank the Space Telescope MIRI commissioning team, the MIRI European Consortium, the MINDS team members, and you all for your attention. Thank you.
Thank you. I think we have time for just one question. Do we have any questions in the room? Okay, yeah, question online.
Yeah, so Bill Green asks, any deuterium?
Well, not yet. Yeah, time will tell, but at the moment, not yet.
Great, any other online? Okay, yeah, quick question online, and then
there is another question by Joel Kastner. Excellent talk, excellent results. Can you say anything about the structure of the inner disk from the strength shapes of the 10 and 20 micron dust features?
Not yet. Again, so this is very much of a work in progress. So we are currently trying to reproduce all the crystalline features. And right now, by including the 5 major protoplanetary dust features, we are already obtaining really good fits, but a lot more work has to be done in order to obtain this information. So stay tuned, for that.
Great, thank you so much. Let's thank Julia again. Shares. Okay, great. So next up, I'm going to give you a
Hi. Yeah.
Okay, so yeah, next up we have Maria Claudia Ramirez, who's going to talk to us about disks on fire. Sounds exciting.
Can I have this? Good morning. First of all, I would like to thank the organizers for allowing me to share the excitement about our new JWST results. And second, I would like to say that I'm talking on behalf of a very big team. We are more than 30 people across Europe and the US, and I would like to highlight some of them. Rens Waters, whose ideas have been the main driver of our project. Then Inga Kamp and Andrew Winter, whose models are the basis of both our proposal and the analysis that we are carrying on. And then Arjan Big from Stockholm University, who has done an enormous amount of work on the data reduction and whose results I'm going to be showing you today. So my name is Maria Claudia Ramirez, and I am a postdoc at MPIA. And today I will tell you about our GEO program, where we are targeting protoplanetary disks in extreme environments. So if there's something that I would like you to remember from my talk, is that thanks to James Webb, for the first time, we are both now able to probe the ability to form planets in extreme environments. And second, that thanks to James Webb, we are now able to learn about the detailed astrophysics of regions that are the analogs of star-forming galaxies at high redshift or very, very far away. So the things that you detect with a single pixel. So I would like to motivate our program, just starting with this very simplified picture of star and planet formation. So you probably all of you have seen this picture before. Stars form in giant clouds that begin to collapse and form clumps, that then keep collapsing and form cores. And then thanks to angular momentum conservation, there are disks that form around these protostars. And in those disks, we form planets. Now, normally, if we want to understand how planets form, we look at these two pictures. And until now, what we have been doing is to compare the demographics of exoplanets. So I'm giving you here an example where you see in the y-axis the planet mass, against in the x-axis the orbital period, and the planets that had been detected until 2020 with the solar system planets. And what we do is we compare these demographics with the physical properties of protoplanetary disks. And the example that you see here is from D-Sharp, all protoplanetary disks in the solar neighborhood. So we take the physical properties of these disks, we compare them to the demographics of exoplanets, and we try to make conclusions about how planets might have formed. Now, the problem is here. So this is a plot that I'm showing you from Andrew Winter and Tom Howard, where what you see in the y-axis is the FUV luminosity, and in x-axis you see the number of stars, and the shaded regions show you the relative fraction of stars in each of these, in the place of this plot. And what we learn from this plot is that most stars actually form in regions like this, where the FUV luminosity is very high because these regions are dominated by massive stars. Now, these disks that I show you that we use to learn how planets form are mostly located in regions like Taurus, at more or less 100 parsecs, regions that are quite isolated and quite quiet, but we know now that this is not the standard form of star formation. So not most of planets didn't form in regions like this. Now we saw, thanks to the first speaker, because he showed us some of the in Orion, where he already showed us that this picture of quiet star formation is not really the standard. But that in Orion, only with one massive stars, you already have these protoplanetary disks that are being irradiated, and you form these prophets. Now, not even Orion is the standard mode of star formation, but we need to find a region that is over there. Now, thanks to JWST, for the first time, we are able to study these protoplanetary disks in extreme environments. So our project focused on NGC 6357, which is the nearest by starburst region, and it contains the most massive star in our galaxy. We target the 15 protoplanetary disks nearby the massive stars to study what the what the physics and chemistry of these protoplanetary disks are. Now, for today's talk, I want to show you two of our main results, the results that we have until now that we are very excited about. The first one focuses on the mirror imaging that you get extra when you do spectroscopy. And the second one, I'm going to show you the spectra of an externally irradiated protoplanetary disk. Okay, so our first result. It is great that when you take spectra of protoplanetary disks, you get an extra mirror image. And we were lucky enough that one of our extra images was pointing at the center of the cluster. So what we detected now when we looked at this image, we were really amazed because you will have all of this structure that wasn't visible before because the Spitzer images are just saturated near the massive stars. If I zoom in, you see these huge proplet-like things with the difference that they are around a parsec across, so 20,000 AU more or less. Now, as I was saying, we thought at the beginning, because of the shape, we called them proplets, but then when we looked closely, we realized they are just much bigger than the proplets in Orion. Therefore, we don't think they are proplets, but more like evaporating gas globules. This is very puzzling, because this is a very extreme environment. This is a lot of FUV radiation. And the fact that these giant monsters are surviving is a bit puzzling. But this is not the only puzzle, because when we looked at the HST images, we see that most of them are detected in H-alpha. So you see here an example. The middle panel, you see that the H-alpha image, you still detect some elongated feature. But then if you look at 850 micron, is not only an elongated feature, but we detect a binary star in the middle. So, yeah, this poses another question, and is that if inside these evaporating gas globules, you even have star formation going on. This it's very exciting because this also means that our pictures of star formation is can be much more complex than we think, because you don't only have the triggered star formation in the larger scales when you have the shocks, but also you might have star formation that is triggered because these evaporating gas globules are just being shocked by the radiation from the massive stars. So we are now working on trying to understand what these central sources are, and we are, I forgot to tell you, Orion has found more than 20 of these structures, and they are all different, and they are all exciting in some way. So we are working on trying to understand what they are and if their properties are related with the distance from the massive stars, for example. And now I would like to focus now on the MRS spectra that we took. So this is what I'm showing you here on the left is the region that we pointed at. We pointed at 15 disks around massive stars. So the stars, the blue stars show you the positions of the massive stars, and the dots show you the position of our sources. And on the right hand, you see in the y-axis, the total FUV that the sources are subjected to as a function of the projected separation to the massive stars. And today I want to focus on this star over here, which is one of our most irradiated sources. Now I'll show you the MRS spectrum. So this is how the MRS spectrum looks like. I thank Julia because she showed you already how a spectrum like this can look in typical T-Tauri stars. This is if you are familiar with this, this looks like a typical T-Tauri star. So you have the big silicate feature at 10 micron, and you have also some phosphorite at 16 and 19.5 micron, and also you see some molecular emission. This was exciting for us because we thought this star was an intermediate mass star, and to see molecular emission is not so common in intermediate mass stars. But then when we looked at the Miri cubes, we realized that we are actually looking at 3 stars that weren't resolved before with Spitzer and 2 mass. So now we don't know a lot about the central source, unfortunately, but we're working on that. Now if I will start zooming in on the features that we see. So we detect some CO. If I move on, we also detect water, as Julia showed you in the talk before. And I can keep moving on where you have C2H2, HDN, and CO2. This was remarkable as well because normally you expect the strength of the CO2 to be related to HDN and C2H2, but in this case the CO2 seems to be weaker, much weaker, which indicates that maybe there is some kind of self-shielding of the other two molecules, for example. Now, what we're able to do now is to model this spectra. So this is similar to what you just saw in Julia's talk. We're able to model the CO at around 5 micron. And very remarkable, the CO is around, so I don't know if you remember Julia's talk, she talked about a couple of hundred of Kelvin. This CO, we need temperatures of around 2000 Kelvin to be able to model it. So the CO is really hot in comparison to other T-Tauri stars. And then, as I mentioned before, we also model the C2H2 and HDN bands. We also detect some water vapor, and our CO2 is much weaker than in other T-Tauri stars. Now, I just want to remind you that we are almost at 2 kiloparsecs. We're doing science maybe for the people who know about protoplanetary disks. You're used to see these things, but we are at 2 kiloparsecs. So this shows us how amazing James Webb is. Now, I would like to finish my talk again with the messages that I wanted to give. We are, for the first time, thanks to JWST, able to probe the ability of protoplanetary disks to form planets in extreme environments, which are the most common environments where stars form. And we are probing the detailed astrophysics of regions that are the analogs of what you see at galaxies at high redshift. And with this, I would like to thank you for your attention.
So much. Do we have any questions? Okay, go.
Hi, thank you. These spectra are just amazing.
Yes.
But I was wondering how this is an analog to high redshift star forming galaxies. Wouldn't you need to be looking at a lower metallicity region to have that analog situation? Or do you plan to look at lower metallicity regions in the future?
Yeah, so this is, we're opening the door to these things. So now what we're showing is that with JWST, you're accessing regions that are quite far away. You're right about the metallicity, but in terms of massive stars, these regions, this is the nearest by starburst region. That's what I meant. Yeah, you're right about the metallicity.
Okay, and one more question. Yep, here.
Thank you. Very beautiful spectrum. So I'm curious about this 2000 Kelvin CO. Can you say a little bit more about where do you think this CO is coming from?
Yeah, so this is obviously we're looking at the inner regions, and then we think this must be like quite close to the central stars. We are not sure if the reason for it to be so hot is because of the external irradiation or just because you are really, really close to the central source. In massive stars, so if the star would be around the 4 solar masses or so, normally this you detect CO at these temperatures, like at a few AU from the central source. But as I said, unfortunately, we have little information about the central source right now.
Thank you.
Hey, let's thank Maria again.
Thank you.
Should we call for like? I think that's okay.
Okay. Where's the? Okay, perfect.
Okay, so I have the pleasure to introduce Brittany Miles, who's going to talk to us about VHS 1256. Thank you very much.
Good morning, everyone. It's a pleasure to talk about only one of the aspects of the JWST Early Release Science program for direct observations of exoplanet systems collaboration. And so I just want to first thank, the PIs and co-PIs of the program, Sasha Hinckley, Andy Skimmer, and Beth Biller, who organized all these things and made sure things ran smoothly. And also people at Space Telescopes and everyone at Space Telescope and everyone in collaboration that helped bring the data that I'm going to show you today together. So I want to first just highlight what's the breakdown of the direct imaging program. So our program 1386, you can look up the status of our observations, but it has 4 components. We wanted to do exoplanet coronagraphy of an actual gas giant exoplanet, disk coronagraphy of a debris disk, and spectroscopy of a planetary-like object VHS 1226b. And then the last program, aperture masking interferometry as well with NearInfrared. I believe the disk coronagraphy program is scheduled for early next year as well. So we're still getting all of our observations. And as I mentioned, I'm mainly going to focus on spectroscopy with NearSpec. I'm using the IFU mode and then the MIRI medium resolution mode. So before I talk about choosing a target, I realize this is a mixed crowd, so I just wanted to go over what a brown dwarf is, how it's different from a gas giant exoplanet. And so, brown dwarfs can be anywhere from like 2000 Kelvin and it can be as cold as 250 Kelvin. So they're really this connection between like the lowest mass stars to even like Jupiter. So if Jupiter was like a brown dwarf, its effective temperature would be 126 Kelvin, and the coldest brown dwarfs are like 250 Kelvin. And at our current like observational limits pre-JWST, in terms of distinguishing a gas giant exoplanet U image and a brown dwarf, they're basically indistinguishable. The layers we're sensitive to in the atmosphere are not sensitive to like, is there a rocky core and then it formed a gas envelope. So we may get there with JWST, but if you just took a spectrum, they look the same. And so we chose VHS 1256b, which is here on the left. So it's a brown dwarf companion and it's not resolved here because this is a discovery paper, but this is a M dwarf binary system, and here's the object here. And VHS 1256b has the same near-infrared colors as some of the HR 8799 planets here. And so on the right, I have the picture of this planetary system we've directly imaged, and it has 4 planets here. This is B, C, E, D. The outer planet B, it's much farther than the orbit of Neptune in our own solar system. So these planets are not only as warm as this brown dwarf, but they're also very isolated and don't have contribution from their stellar companion and influencing the infrared spectrum. And so the goal of this program is to get IFU spectroscopy from 1 to 28 microns for VHS 1256b. And so we want to do this to understand, what molecular features appear in these gas giant atmospheres, what kind of clouds form. This will help us better inform, what observations do we need to do to understand gas giant exoplanets when we image them in the future. So I just wanted to lay out what were our capabilities, pre-JWST. So this is a plot from Dinaro Suarez where there was an analysis from 1 to about 10 microns of this, T dwarf that's about 1000 Kelvin. And so in the near infrared from like 1 to 3 micron, it's pretty standard to be able to get spectra. With HST, we can get really low resolution water bands that are hard to get from the ground. But for very cold brown dwarfs that have like a J band magnitude of 20, you're not getting very good high resolution near infrared spectroscopy. And then, so this is 1, 2, 3, yeah. From 4 to 5 microns, there are some mid-infrared spectra, but it's very hard to get from the ground. And very few brown dwarfs have M-band spectroscopy from 4 to 5 microns because one of the limitations of our infrared windows from the ground, and also is just a lot of sky background. So it's very challenging to get that spectra there. And then with Spitzer here, you're getting a resolution of 60 out to 10 microns. And so there's all these features here, but you're either limited by Earth's atmosphere or you're getting it at a very low resolution. So this is the JWST spectrum of VHS 1256b. All the bands all the near spec filter grading combinations are labeled, and so are the MIRI channels labeled, well, all the 1, 2, and 3 are labeled together. And so we have a spectrum from 1 to about 20 microns. Channel 4 was very hard to get a signal, so we compiled that into a single photometry point for this plot here. And this research has been accepted as like a week ago or something, and I'm just listing the JWST pipeline and CRDS context because our data reduction is public, and I would like people to revisit these when we actually get near spec flux calibrations that are sponsored by the team. So to get this flux calibrated spectrum, I had to reduce our ERS data and I reduced commissioning spectroscopy. And so basically you reduce the A-star spectrum, you see where are there deviations from the model spectra, and then you apply a scale factor for each filter grading combination to match the spectrum to MIRI. So one thing I'm proud of is that between near spec and MIRI, we get pretty good overlap, even with their error bars for both our instrument modes. And I'll go through the spectrum part by part, but there's still good continuity between these different filter grading combinations and even between detectors. Yeah, it looks awesome. And also, one parameter that brown dwarf people care about is the luminosity. So brown dwarfs, they don't fuse energy, they just have the heat from formation and just cool over time. So basically 99-point-something% of the luminosity is enclosed in all of the wavelengths accessible to JWST. You're basically gated by the distance measurement to get that luminosity. Okay. These are just, I'm going through the spectra. So these are the near-infrared spectra. On the bottom, I have VHS 1286b plotted in black. And on the top, I have some template brown dwarfs that are, older, objects that have really high gravity. And so sodium and potassium have these absorption features at these wavelengths. And then these features are very deep because these brown dwarfs have very high gravities. VHS 1286b is a very young brown dwarf, just like the HR 8799 planets. So these features are very muted compared to, relatively normal brown dwarfs. And so this is just the same spectrum plotted again with the 1.5 to 1.8 micron feature. And so you have a very clear water absorption feature between the two detectors in this filter grading mode. And water is very key in constraining, the overall abundance of like where the oxygen is for, this atmosphere. And then the next portion of the atmosphere, we still have more water here. This is where some of the instrument artifacts really affect our spectrum. These are the oscillations that appear when you create an IFU cube with the near spec mode. You can still see the big absorption band from CO, but some of the other lines you would typically see are affected by these oscillations you have in the spectrum. And also you have more water from 2 to 3 microns, with some really nice lines here as well. And I'm looking forward to see how this portion of the spectrum is updated with more information. So this feature here from 3 to 4 microns is mainly due to methane in the atmosphere. And so on the top, I have the opacity of methane plotted. And so where you have a peak, you should have a dip in our spectrum here. And you can see the peak of methane here. And it's a very nice feature. If you were to do this from the ground, there would be a very high error bar here, because I've done this before myself. But here, this feature is very clear. You can even see some of the wings of methane very clearly here. For this particular brown dwarf, this methane feature is quite shallow. So what this tells us is that there's warm CO gas being brought up to the upper levels of the atmosphere, and this methane feature is depleted. And so this is a very clear signature that there's non-equilibrium chemistry driven by convection in this brown dwarf. And so this is one of my favorite. Also, there's error bars plotted on this plot. They're just very tiny. Yeah. Yeah. From 4.2 microns to 5.2 microns, you have a really good CO feature that really mirrors the opacity of CO for this specific temperature of the atmosphere here. And these combs are beautiful. And so there's probably a lot of more work you can do with this feature itself CO, for this particular brown dwarf, CO is so abundant that disequilibrium chemistry is not, 2 more minutes, thank you, is not affected at this temperature, but for colder brown dwarfs, you could see shifts based on that mixing as well. It's not labeled here because we were trying to eke it out with modeling, but CO2, we did some atmospheric modeling that showed you would need CO2 to match some of the slopes here, but we didn't claim a detection. That's more work that needs to be done. And then this is the MIRI spectrum here. We can start to see the error bars a bit. And the dominant feature here is actually the bin from the silicate clouds. So brown dwarfs that are this temperature have silicates in their atmospheres that also affect the near-infrared spectrum. And the shape of this silicate feature can also tell you, is it forced right or is it instatight? What kind of particle sizes are those clouds? So there's much more to be explored here on, why this feature is shaped the way it does. Out here, the SCD is mainly influenced by water, and then there's some methane in water here as well. And then this is just a comparison between other brown dwarfs. The data is plotted in gray here, and the template spectra is in blue. And so this brown dwarf is relatively cloudless, and you can see the clear dip from the silicate feature from VHS 1206b. And in the Spitzer spectra, you can see that they match up nicely when compared to a cloudier object. In conclusion, from this spectra alone, we know some things about the objects that we've seen before. We know it's a young, cloudy planetary mass companion. Beth Biller did an analysis of the luminosity that says it's from 12. It can be anywhere from 12 to 16 Jupiter masses, but it's leaning more towards 12, which is below the deuterium burning limit, which is why we called it planetary mass. And the spectral features show that the atmosphere is out of chemical equilibrium due to atmospheric mixing. And then, this took about 2 hours, I believe. So JWST has the capability to characterize brown dwarfs this well with a signal to noise per pixel of like 10 to 400 for a lot of other brown dwarfs. And I'm excited to see where the community takes this. So with that, I'll answer any questions. Thank you for your time.
I'm not biased at all. Okay, do we have any questions online? I'll take one online.
Yeah, there is 2 questions online. One from Joel Kastner. Stunning to see this reach 1 to 20 micron spectrum of a young brown dwarf. Can you remind us what's the age of VHS 1256b? Is it as young as HR 8799?
I would have to look up the exact date. I know it's like a couple 100 million years old, right? Yeah. But I'll post in the Slack the actual paper so that we know. Yeah.
We have a question right in the middle there.
Hi, Will Best, University of Texas. I love that spectrum. Thank you for sharing it with us. And great work. This is a really dusty brown dwarf. I wonder if you can say anything yet about the dust grains, their shape, their composition. I saw silicate, but I'd love to know more about that if you've been able to do anything yet.
So we haven't been able to. So our modeling group prescribes to the FSED philosophy of so. With that, there's a parameterization of the specific grain size and what the shape of the cloud is. But I don't think we've done any work to say, like, we're going to only start with something that's 1 micron and see, like, what's the difference. So I think that's more exploration we can do. Another thing that's been an issue with this, it's very hard to actually match the cloudiness, but not mute the features out. And so I think we need to explore about, like, where the clouds actually are. So it's a really big issue with fitting the spectrum, yeah.
Okay, let's thank Brittany again. Okay, so next up we have Kevin Stevenson, who is going to tell us all about the Transiting Exoplanet Community ERS program. Take it away.
Thank you. It is really an honor to be here today on behalf of the Transiting Exoplanet Community Early Release Science Program. Many people don't know, but it was 7 years ago in this very room where the seeds of this program were first planted. I was standing at this podium back in November of 2015, making a pitch to a bunch of exoplanet astronomers about this exciting new community initiative called Early Release Science. And as you can tell, I think the community bought in fairly well. 7 years later, here we are. These seeds have grown into a tree. The tree has blossomed, and it is now bearing fruit. And I think we can all agree that the fruit from the JWST tree tastes very sweet. So here we have the community as it was in, I guess, 2018. We started off with a fairly small group, a dozen people or so. First publication had about 50 co-authors. By the time we submitted the proposal itself, we had grown to over 100 people, 60 investigators, an additional 50 collaborators. Today, we're at over 350 investigators on the team. We are open collaboration. Anyone who wants to join and participate and agree to the code of conduct can do so. And it has been a very interesting experiment to conduct on a community-wide basis for this particular project. So here I can tell you a little bit about the amount of time that we have and the science goals for this program. We received 80 hours of JWST time. It was broken down into 3 science objectives. The first one program is the panchromatic transmission program. Here the idea is to study a single target in transit using 4 different instrument modes. And what we wanted to do was understand each of these near-IR instruments to the point where we could have overlapping transmission spectra, then determine the reliability of these results. Next, we have the MIRI phase curve program. In this case, we're observing, again, another target using 3 different types of observations: transits, eclipse, and phase-resolved emission, or a phase curve, using the MIRI instrument. And here we can actually assess the reliability and stability of MIRI as we perform a long 25-hour continuous observation of a single system. And finally, we have the Bright Star Planet Emission Program. This is looking at a very bright target, Kmag of 8, I believe, approaching near saturation. And here we want to assess the noise floor of the instrument. This is key when we're looking at, for example, rocky planets. We need to be able to determine how well we can stack all of our transits together in order to determine feature sizes that are perhaps on the order of 10 parts per million. Okay, so let's focus in on this first program. And before I show you real results, I want to show you the simulated spectrum from our paper a few years ago. And what it did is it used HST-WFC3 spectra from the G141 GRISM, and we essentially extrapolated the result to shorter and longer wavelengths, spanning the full instrument wavelength range. And when I looked at these results, I thought, well, gosh, gee, I mean, this is a dream, right? I can't wait to have this type of spectra. And now the dream has come true. This is the NearSpec Prism transmission spectrum of WASP-39b. It is a hot Jupiter around 1200 Kelvin. We have a large number of spectroscopic features. Before, we could only detect water with Hubble and a few other species. Here we have sodium, water, carbon monoxide, carbon dioxide, and sulfur dioxide, which I'll get to shortly. Now you can see this is fairly low resolution, and it was a good test because it provided full wavelength coverage from about 0.5 to 5 microns that we could then compare to our other instruments. Here we have NEARIST, which is a higher resolution, but doesn't span quite the same wavelength range. Again, we've detected water, multiple water absorption features, which is key. But we've also detected another species, potassium. This is something that's been a little bit shy for us in the exoplanet community. It's been really difficult to pick on potassium, in part because it's very difficult to observe from the ground due to tellurics. So the fact that we've seen it here from space is going to be a huge boon in the future. Next, we have NearCam's F322 double wide filter. And this may seem a little because we're only detecting water. But what's interesting about the spectrum is that we haven't detected methane. We would expect, given the equilibrium temperature of this planet, that we should detect that 3.3 micron methane feature. But we're not seeing that. In fact, it's been very difficult to see methane in any transiting exoplanet. And so what that's telling us is that there's probably something going on in the atmosphere, likely photochemistry, spoiler alert, that is removing the methane from the atmosphere and converting it into other species. And next we have the NearSpec G395 GRISM. Again, higher resolution, spanning about 2.5 to 5 microns. We have these similar features here. The first definitive detection of carbon dioxide in the transiting exoplanet atmosphere. And we also have this beautiful SO2 detection. So this sulfur dioxide detection was a bit of a surprise to me, and I think to a lot of people in the community. It was one of those unexpected, oh, what's that bump right there? What's going on? And then, of course, all the theorists dive in, and they build a huge database of all the potential molecules that this could be, and then they slowly rule them out. And the list got whittled down, until only one species remained, SO2. And so it was a fantastic discovery. I highly recommend that you read the paper. The process itself is much more complicated than this, but essentially the idea is that you have the photodissociation of water, breaks it down into its components, interacts with hydrogen sulfide through a chain of reactions, and then in the end you produce sulfur dioxide. You've got the net reaction on the bottom there, as you can see. So here we are today. We have our 4 individual transmission spectra of WASP-39b, and the question is, where do we want to go from here? Well, of course, our goal was to compare the transmission spectra of each of these modes to make sure that they overlap, to see that we're achieving comparable results. So the previous 6 papers have all been published, but now I'm showing you future work. Here is the overlapping transmission spectra from all of these planets. We have not applied any sort of offset at this time. And as you can see, they overlap remarkably well. All of the bumps and wiggles from the water, the CO, the CO2, they all really sort of match up. We're still resolving some minor issues in terms of the alignment. We're making great progress on this. And once we do that, we'll be able to perform a full atmospheric retrieval, obtaining molecular abundance constraints on all of these major species in the atmosphere to very high precision. This is, on the order of 0.1 to 0.3 dex per species, which is essentially an order of magnitude better than what we've been able to do with Hubble to this point. All right, next let's move on to the MIRI phase curve program. I should tell you that these observations were made less than 2 weeks ago. So this is very preliminary. None of this is published, so please don't share this moving forward. Before we actually jump into the data itself, I want to step back to 2014, where we performed the first phase curve observation, spectroscopic phase curve observation of this planet, WASP-43b, using Hubble's WIFC-3. And just to orient people those aren't familiar with a phase curve observation, we've normalized it so that the stellar flux is at 1, and so that anything above 1 is contribution from the planet. And we're observing the planet as a function of orbital phase or time. So we have the transit at a phase of 0. It rises up, where we have the secondary eclipse. You got the peak flux occurring probably a little bit before the secondary eclipse, and then it goes back down again towards transit. And so this is essentially the day side of the planet that's highly irradiated, coming into view, being eclipsed by the star, and then fading away. And what's interesting and unexpected about this planet is the night side flux was essentially 0. We couldn't measure any emission from the night side. So of course, when you can't measure the emission, it's probably because it's too cold, likely high altitude clouds, and we can just move to longer wavelengths and hopefully detect the thermal emission on the night side there. So we did that with Spitzer at 4.5 microns. This is oriented a little bit differently, where we've got the eclipse, the transit, and the eclipse here. Sorry for the change, but the point remains the same. We observed the phase variation, and again, on the night side, we could not measure the planet's flux. So it was even cooler than we expected. All we had was essentially an upper limit of what that temperature could be. This is the MIRI phase curve white light curve from 5 to 12 microns. And you can see we have beautiful eclipses, transits, and eclipse itself right there. Just doing a fit by eye, because today, actually, at this time, people are meeting as part of the ERS team, comparing results online to see how well every reduction has done. I'm just showing you the basics right now. But I can tell you that we see a short ramp at the beginning here. This is not particularly uncommon to see especially in the Spitzer phase curves. And I've fit a little slope right here just to guide the eye to see where the night side emission is. And sure enough, it looks like we're actually detecting thermal emission from the planet on the night side. So this is really exciting. I look forward to seeing the results moving forward. And please stay tuned. I think we'll have more results at the JWST conference in January. Finally, let's move on to the Bright Star program. Again, these observations have not been published yet. So please don't share them, but the paper has been submitted or will be this week, so you can look forward to seeing that result here. This is just an eclipse observation, but you can actually see the phase variation of the planet, even though it's only a very short. So this is actually really exciting. We can see the peak flux of the planet there shortly before the eclipse, and there's also a little bit of curvature during eclipse, which was surprising to me. Turns out it's ellipsoidal variation of the star itself. So we're actually seeing WASP-18, which is a 10 Jupiter mass object, deforming the star itself. As it goes around, the planet or the star itself is not spherical. Of course, we have an emission spectrum, but I won't be able to share that with you today. But I will be able to share with you this plot that, if you're not familiar with it, can be a bit confusing. But the main takeaway point is that we can achieve a very precise 5 ppm precision on 60-minute time scales. This is our test of the noise floor. We can basically compare the theoretical expectations, which is this red dashed line, to the actual noise that we measure at various time scales, which is black. And we do have some noise at 5 parts per million, or sorry, at 5-minute time scales. But at the 60-minute timescales, everything seems to be working out well. We're sort of integrating over that red noise. And this is particularly important when we talk about detecting or characterizing rocky planets around nearby M-dwarf stars, because the timescale of the transit is on order of 60 minutes. And so you do not want to be seeing red noise at that timescale, because you will not be able to take dozens and dozens of transits and bend things down as you expect. So this is a real exciting result that we've gotten here, and we've actually validated it for both NearIS and for NearSpec. And I have a bit of a surprise since I've got 30 seconds left here. This is not part of the ERS program. This is another program where we observed 2 transits of a rocky 1 Earth radius size planet with JWST. These are the white light curves. So this is a 1 Earth sized planet around a nearby M-dwarf star. It is exciting results. It is perhaps the first discovery of an exoplanet by JWST, in the sense that it was originally a object of interest, and then it was validated with JWST with these observations. So we know it's a planet. Please stay tuned. We will have more results at the JWST meeting in January, and I look forward to seeing you there. I will stop and take your questions. Thank you.
So much. It's so exciting. Do we have any questions? Are there any online? Any in the audience? Absolutely.
Will you tell us the period of that planet? Like, is it a habitable zone?
The period of the planet is about 2 days, so it is more like an exo-Venus than an exo-Earth, 500-ish Kelvin.
Thanks.
Marshall over there.
A comment more than a question. You may have already thought of this, but the excess noise at the 5 minutes is potentially the telescope wavefront error from the instrument electronics heaters cycling on and off, which is a 3 to 5 minute time scale.
Thank you, Marshall.
We can chat.
Okay, let's do that.
And talk with Everett as well, who's been looking into this in a lot of depth on the NearCam side.
Okay.
Okay, were there any last questions? Keelan, did you have your hand up? Go ahead. Last question.
Hi, I'm Keelan Hook, fellow here at Space Telescope. I was wondering just about the the pipeline and using NearSpec and everything. Has your spectra changed with all the updates to the pipeline?
So we are using multiple custom pipelines for the data reduction. Some of them rely on JWST stage 1 and stage 2 reductions, but then basically from there we move off to our own. There are probably a half dozen different pipeline reductions right now. But the good news is all of them tend to agree. So that, regardless of the calibration that's been used for the instruments, we're still getting the same results. It's just kind of fine-tuning the individual data points. So at this point, I think things are going really well.
Great, and I think we'll end it there. Let's thank Kevin again. We're moving into our final talk of the session. Last but not least, we have Claudia who's going to talk to us about a Dwarfs spectrum, revealing its cool molecular features.
Thank you very much. Hello, everyone. It's very cool to be here and see all this great science we've been doing with JWST, and I'm happy to close this session with a very interesting object. And I want to start with saying that this is work done by the MIRI GTO group, and especially the Exoplanets GTO group. And I want to highlight here the persons that are doing most of the modeling, and especially Paul Molière, who provided all the models that we show you today. So generally coming from exoplanets, and as Brittany alluded to before, I've been quick to dismiss brown dwarfs as, the low mass end of star formation. Who cares? We want to do exoplanets. With new data, we should update our kind of positions. I've been very interested, and I'm changing my kind of thought on what brown dwarfs are in the context of exoplanets and research of atmospheres. So I think the brown dwarfs will be a crucial piece of the puzzle when we want to explore the connection between the gas giant exoplanets, for example, being directly imaged, and connecting them to the solar system planets. For example, the main thing about Jupiter, that are cool gas giants, and we want to understand how they form and what the atmospheres do as they age and cool down. So brown dwarfs kind of have the best of both worlds. They have this exquisite data quality, or much better data quality, that like the information we can gain from the solar system planets, but they also provide a huge diversity that lets us explore the demographics of planet formation and connect them to the few and technically much more challenging observations of directly imaged planets, and of course their closer migrated hot Jupiters, for example. So I like this plot because it kind of gives a big image of what is going on. There's a big range in parameter of brown dwarfs, and generally brown dwarfs and giant exoplanet atmospheres are very similar to all intents and purposes. So we can see here this plot by Cushing, that how the spectra kind of evolve as a function of temperature. And we see these spectra are beautifully dominated by molecular absorption features that tell us a lot about the composition and structure of the atmosphere. And this is what we really want to understand. How do these atmospheres work fundamentally? And brown dwarfs are an excellent laboratory for exploring this question. And I want to focus your attention here. So as brown dwarfs cool and we get to the more interesting, everything is interesting, but more closer to Jupiter, let's say, in really trying to nail down and make connection with the things in our own neighborhood, we see that everything moves kind of to the mid-infrared here. And as Brittany showed before, we gain a lot of information by looking at the spectrum in the full luminous range here, but for cold objects, more than 90% of the luminosity is really just concentrated here in the mid-infrared region. And again, I want to put your attention to that the dominating absorbers in this atmosphere also change with temperature. As planets cool down, different molecules become more important, especially ammonia. Ammonia is observed in Jupiter and is very hard to get in the near-infrared, and this is why we're really excited to use JWST to actually access these kinds of atmospheres and characterize their chemical composition in detail. And so let's talk about WISE 1828. This is the first of its kind, meaning that this brown dwarf was discovered in 2011 by Mark Cushing using WISE, and it was so different than the previous spectral type that it warranted kind of a new category of its own. And this kind of type of brown dwarfs, here you see a Spitzer an HST spectrum. They are dominated by methane and ammonia. So the predominant change between the previous spectral type is really the existence of that ammonia dominates everything. And this is really now oven temperature of 350 to 450 Kelvin. This is getting very interesting. And this type of brown dwarfs were just not possible to look at with Spitzer because they were actually discovered after its cold campaign, and the sensitivity wasn't there. So this is the best spectrum we have of a white dwarf, brown dwarf, of the WISE 1828, again taken by Spitzer and realized by Mike Cushing recently in 2021. And you see here, you see this methane absorption, water absorption, and a tentative kind of hint that ammonia is there. And generally, ammonia has been shown to be there indirectly, just to explain kind of the color, the full SED, when we look at also the Spitzer photometric points and the WISE photometric points. Generally, check out Ben Liu's poster on the near-infrared data of this object we also got last July, this July actually. So now I'm going to show the MIRI data we got. This is the image of the cube, processed cube, where because it's such a faint source, we can just do classical knot subtraction, and it works quite well. You see the background is nicely gone at this wavelength. You see the brown dwarf in the middle here, and the two negative PSF from the dithered knot subtraction. And so, again, to put a bit of a perspective, this is from a recent study by Suarez and Metchev, and they did a systematic study of brown dwarfs with Spitzer. And you see in their paper, it's very nice to see the change when you go from hotter brown dwarfs to cooler brown dwarfs, which this is kind of the best we could do with Spitzer, this kind of T6 brown dwarfs, where you start seeing this ammonia feature here. And this is exactly what we want to characterize and understand better. And now I'm going to show what we get with MIRI. And this is the ammonia feature we get with MIRI. This is really orders of magnitude in improvement in what we can do to characterize in detail this molecular absorption band. And this is not noise. I was actually coming from 6 months of commissioning. My head was still in distortion and photometric calibration, which is complicated with an IFU. But and I thought something was off with some of our calibration steps, that is somehow missing the source and the source is moving. But yeah, then just by comparing with the model, we realized these are actually really expected features of ammonia. And here's the full spectrum. There's so much more to explore. This is a 5 to 18 micron spectrum. Again, channel 4, we lose a lot of sensitivity. We get some signal, but for now we kind of leave it out. But I think, and this is purely dominated by molecular absorption. We have not found any hints of clouds in our first analysis. And here I show a bit kind of the molecular bands that dominate the different regions. Here's the big prominent ammonia feature in the middle, the water absorption in the shorter wavelengths, and the clearly detected methane feature. And in the end, again, we're dominated by water absorption features. Okay, so I'm not going to talk too much on the modeling. It's not really also my expertise, and you should look up. So we are preparing a paper on the first results led by a great team. But Paul and me, we looked at some models, and I'm actually plotting the model behind the spectrum here, which is a bit unfair. And this model is a 1D radiative transfer model, which we have kind of used our best parameters with a simple first fit And now I'm transposing the model to actually show that this is what we actually expect. And it is amazing that we can really now actually start resolving these tiny features that will inform us about the structure and place great constraints on the molecular abundances of this atmosphere. And to finish, I just want to present the spectrum and kind of create excitement about cool brown dwarfs and spark discussion on how we can do better now. And this really challenges our methods that we are using at the moment to fit these models. So Paul came up with this way of trying to kind of give you an insight on how cool the spectrum is. And here what I plot is, this is the lines where we expect absorption from ammonia, and kind of the width of the line. The vertical lines here show the kind of the strength of the absorption feature. And if you now go and we have a video of this going through all different molecules, but I'm just trying to concentrate here on ammonia. You can just go along the spectrum, part of the spectrum only here, and you see that every line is reproduced. And there are some wavelength errors which give me still a job to do, to improve. But you can see even like the faintest features are real, and you can also see kind of like beautiful overlaps between the orders of the bands of the MRS, which was a big worry for us going into commissioning, that we nail this down. And you can just stare at this spectrum and explore this small all these small features, which most of them are identified, and we actually find quite interesting, quite good agreement, and with just a few lines that we have not identified yet. And so, yeah, it's kind of concluding already. I just want to share this beautiful and demonstration that the MIRI on JWST can really go after these cool objects. And there's a mid-infrared opportunity here. Nothing will replace this instrument in the foreseeable future. And we should go after more cool brown dwarfs and also the cool exoplanets, that then we can draw connections to this beautiful spectra here. And I want to thank my colleagues and everyone that worked on this mission. And I'm very excited to learn much more about science as we proceed into more science operations. Thank you.
Incredible. Do we have any questions? Any online? One? Okay, yep.
So we have a question from Bill Green. Does any space system have high-resolution far-infrared detection capabilities?
Sorry, I didn't get the question.
Does any space system have high-resolution far-infrared detection capabilities?
I don't think so. So this is really the MRS. This is what it was built for. We really want, as you saw also in the talks today, we really want to understand that this is the best resolution we will get for the mid-infrared. At least, certainly longer than 7-8 microns from space.
Okay, in the interest of not standing between this and coffee, mostly for me, we will end here. So let's thank Polychronos and all of the speakers in this session.
Thanks.
We will be returning at 11 a.m. Eastern for those online, so in about 25 minutes, so go and enjoy your coffee.
Yeah.
Is it on?
One quick announcement. If anybody's trying to organize travel back to airports or train stations, you can work with the events planning people at the desks. And so go talk to them or send them an email.
I stopped sharing the screen. Oh.
Hello? Hello? It's not gonna.
Tap it? Oh, yeah, it should be green. Just there, yeah.
Hello?
Yeah, that works.
All right.
Do you want me to wait a minute, Chris? Or is the sound of my voice sort of getting winded, I think.
Yeah. No, I am.
Great.
Share.
Did you want me to wait a minute still? All right. Okay. And that time's like a little bit ahead for a few minutes. So use it for as like
Okay.
talk for 12 minutes rather than like, oh.
Look at that clock. Yeah, okay.
But I'll give you the 2-minute warning.
Yeah.
Yeah? Go now? Session 8, Assembly of Galaxies. Yeah, galaxies. Yeah, good. All right, so it's my pleasure to be chairing the next session. We'll be continuing on Assembly of Galaxies from Monday. And our first speaker is Timothy Carlton, talking about ultra-diffuse galaxies in the El Gordo cluster.
Thank you, yeah. It's really been an honor to sit here and like listen to all the great talks that are describing all these great results from this observatory. And again, I'm grateful for all the work that everyone's put into making all this happen. It's really amazing to see. So yeah, I'm Tim Carlton at Arizona State University, and I want to talk to you today about ultra-diffuse galaxies, or UDGs, in the El Gordo cluster. And this is work I'm doing as part of the PEARLS, or Prime Extragalactic Areas for Reionization and Lensing Science program. That's PI by Roger Windhorst at ASU. I don't have time to talk about lots of all the cool stuff that's going on in PEARLS, but I would definitely encourage you to check out Mini Hyun and Hao Jingyan's posters that also are talking about some PEARLS results. But yeah, we've got a lot of cool stuff. We've got nearby galaxies, distant galaxies, galaxy clusters. So yeah, check it out. So yeah, first I just want to kind of step back and talk about what I mean by ultra-diffuse galaxies. These are really, I just describe them as unusually large dwarf elliptical galaxies. These are, you kind of look at this full space of stellar mass and half-light radius for elliptical galaxies. You see that there's kind of these massive ellipticals all the way down to dwarf ellipticals, and then we've got some really just unusually large galaxies that really seem to kind of be significant outliers from this kind of global relation. And these are galaxies that have been known for almost 40 years now, but really they kind of received a resurgence in interest back in 2015, where a large population were discovered in the Coma cluster with Peter Van Dokkum's Dragonfly survey. And yeah, they're kind of unusual, and they I think they can kind of really give us some insight into how dwarf galaxy evolution unfolds in general. So yeah, like I said, they're primarily identified in galaxy clusters, though some have been identified in the field. And one thing that I think is really interesting is that a number of UDGs seem to have unusual dark matter halo properties. So here, this is halo mass on the y-axis and stellar mass on the x-axis. And we have a few like non-UDG points with some kind of following along some abundance matching relationship. And then you have some of these ultra diffuse galaxies that really, again, just seem to be outliers from this relation. You have things like GF44 up here with like 10 to the 11 and a half, 10 to the 12 almost, the halo mass. And you have something like GF2, which is very similar. If you just kind of look at it, it has a similar stellar mass, a similar size, but halo mass that's consistent with having no dark matter at all. There's been controversy about all these different measurements, of course, but I think it's pretty well understood that there's a wide range of diversity of galaxy properties for something we thought is so fundamental as something like a galaxy's stellar mass. Why are we getting such a wide diversity of properties? I think this is really a great opportunity to kind of better understand dwarf galaxies and how they form and evolve, because really there's something going on here. And so ever since we have these interesting galaxies, we've got a lot of observations of them kind of in the local universe, and we have some kind of general properties of what they look like. And interestingly, a lot of the time, they seem really similar to other non-UDG galaxies. They're kind of follow the red sequence, generally, quiescent galaxies in these clusters. They kind of tend to live in a similar place within the cluster as non-diffuse dwarf galaxies. They're kind of elliptical in shape, and their abundance kind of scales with the mass of the cluster. But when you kind of look in a little more detail, you're starting to see some differences. For example, here, this is the kind of surface density of galaxies as a function of cluster-centric distance. And for kind of normal galaxies, you kind of generally follow you generally increase all the way towards the cluster center. But for ultra-diffuse galaxies, you kind of hit this plateau and kind of run out of galaxies in the center. And this is generally interpreted as tidal effects kind of destroying these diffuse galaxies. Similarly, if you look at the axis ratio distribution, while it's generally kind of round and elliptical-like, similar to non-UDG dwarfs, there is some signature that is kind of more stretched out than kind of these non-UDG kind of round galaxies or disky like. And so we have all these observations to kind of get an understanding of how these types of systems could have formed. And of course, we've got lots of different ideas on how to form these diffuse galaxies. For example, if you're a big fan of some recent hydrodynamical simulations, you think that stellar feedback is really important, you could have really diffuse galaxies naturally come out of those simulations. Or maybe there's some cluster-specific feedback. You can imagine if you're just in a high angular momentum halo, then you kind of get this distribution of larger galaxies. Or maybe there are some environmental effects at play, like ram pressure stripping, or the specific merger history, or tidal interactions within the cluster. And all of these are kind of consistent with some, but not all of the observational properties that we see in UDGs today. But I want to kind of highlight these bottom two as really environmental processes that we would expect to depend on redshift. So these things are saying that if we look at higher redshift diffuse galaxies, we would start to see some differences. You could argue that maybe feedback would also fall into this category, but maybe not as much. And so really this presents an opportunity to kind of test our understanding of the formation of dwarf galaxies and ultra-diffuse galaxies by looking at higher redshift clusters and higher redshift galaxies. This is kind of where we can start to look towards JWST. But before we get there, just want to highlight that some work has already been done starting to kind of probe larger and larger redshifts. And I mean, as I'm sure most of you in the room will know, a lot of great JWST projects are built on great HST projects that kind of pave the way. And so I want to point out Janssen et al. And I didn't put on the slide, but Lee et al. Looking at ultra-diffuse galaxies in the Hubble frontier fields. And they were able to identify these UDGs. And generally, again, kind of seeing not too much of an evolution in their properties. So we have all these frontier fields clusters. They generally kind of still follow this scaling relation. And for kind of the low redshift, we're still kind of seeing this effect where there's a deficit of UDGs in the center. Maybe not so at kind of the higher redshift, but we're still generally consistent with what we're seeing in the local universe. And so here's where we kind of were before JWST. And then we can go out to look at the El Gordo cluster. So this is not the JWST image, but this is the relics image of El Gordo. This is a massive cluster at redshift 0.87. And it's really interesting in its own right, possibly in tension with Lambda CDM, but it's, because it's so interesting, it was targeted as part of this PEARLS program. And I kind of saw this and was like, well, maybe we can look for these ultra-diffuse galaxies at this kind of unusually high redshift and see if we can better understand these dwarf galaxies kind of beyond where we've been able to do so before. And so within the JWST imaging of this cluster, which we got back earlier this year, we were able to identify some ultra-diffuse galaxies. We identified over 500 in the El Gordo cluster in parallel field, and here I'm just showing kind of cutouts of a few, and you can, see that there, like, we've got some of these kind of dwarf smudge-like things that we're able to kind of study and try and understand with this kind of brand new excellent instrument. And so once we have these images, we can start to look at some of their properties and kind of better understand these systems. So for example, if you look at the axis ratio distribution, where this is kind of the distribution of the blue is the axis ratio distribution for UDGs in the cluster field, and compared with some low redshift analogs. And we are starting to kind of see some differences where UDGs in El Gordo seem to be a little bit more elliptical than kind of their local counterparts. And where kind of, if you look in coma, kind of the distribution rises to a certain point, and then kind of you're not seeing a lot of face-on systems. But in these El Gordo UDGs, we're seeing kind of more of a flat distribution. And then also, one thing I was particularly interested in looking at is the color distribution. So this is the distribution of the 200W minus F277W color. And what we're finding is that the UDGs in the cluster actually seem to be a little bit bluer than non-UDGs in the cluster. And it kind of extends further, where if we look at kind of larger, kind of the largest range of UDGs that we're finding in the cluster, they again seem to continue to be bluer. And again, this is suggesting maybe these are kind of more recent infalls into the cluster, and maybe the tidal effects that are important for lower redshift UDGs haven't had time to impact these systems. And we're still we're doing some kind of more detailed SED fitting to kind of fully understand what's going on here, but it does seem to suggest that maybe there is some redshift evolution in these systems. And so with that, I'll just kind of put up my conclusions. We've got JWST is capable of studying these kind of low surface brightness, ultra diffuse galaxies kind of beyond the redshift we've been able to do previously. And we're starting to see some differences kind of at redshift 0.9 or so compared with what we're seeing locally, suggesting maybe there is some evolution in the types of galaxies that make up this UDG population, or kind of the formation of these systems. So with that, thank you. I can take any questions.
Are there any questions online?
No.
Otherwise, in the audience, yeah.
Hi, thank you for your talk. I was wondering if you could I didn't quite understand how you go about finding or selecting the ultra-diffuse galaxies in your sample.
Yeah, so I basically used a stellar mass density and size selection, and so I selected it based on the kind of stacked FO90, just kind of stacked all the bands we could get, and kind of based on some rough expected mass to light ratio, kind of got some, looked at the kind of surface brightness, the average surface brightness, and the size based on some Galfit results, and then yeah, that was kind of how we selected them.
Oh, there's someone in the back.
Nice work. Yeah, great to see this work coming out of pearls. Yeah, I guess you kind of alluded to, you might imagine that these, diffuse galaxies are kind of, you imagine a spiral coming in and getting disrupted, and then, maybe it turns into something like this before maybe getting more compact like the other galaxies. And you showed these seem to be bluer than the other ones. And I guess the next step, like you said, is the SED modeling. We can measure masses and ages for the first time, and not only in this cluster, but in all the clusters from Pearls and other programs. So maybe that's the idea.
Yeah, definitely. I've been focusing on this cluster because it's really just kind of pushing the redshift boundary of what's been seen before. But yeah, looking at the other clusters that we've got, even at lower redshift, to kind of better understand their properties is definitely something I have in mind.
Susan, were there any questions online?
No questions online.
Call for questions. All right, if not, we'll thank our speaker again. So we're going to continue on with the next speaker, Sean Linden, who's going to try to be revealing hidden star formation in VV114, and I hope you do it.
Thank you very much. Thank you for the organizers for giving me the opportunity to speak to you all today about some of the work that we've been doing in the Great Observatory's All-Sky LERG Survey ERS program. I'm going to talk to you today about some of our results for one of the four systems, VV114. And I just want to pause on this title slide for a second, because when the NearCam observations came out in August, we actually got flooded with amateur astronomers sending us their own Photoshop renditions of the galaxy. And I have to tell you, these people are far more talented at making pretty pictures than I will ever be in my life. And so this is just one of the many beautiful images that the GOLS team was sent in the first month. And I just want to give credit to Braden Butterfield. If you're listening, Braden, your image is beautiful. All right, so the Great Observatory's All-Sky LERG Survey is aimed at studying the properties of local luminous infrared galaxies. And while local luminous infrared galaxies are rare in the nearby universe, it turns out that at cosmic noon and higher redshifts, luminous infrared galaxies, or galaxies with an infrared luminosity greater than 10 to the 11, actually dominate the infrared density of the universe. So these kinds of systems become much more representative of high redshift galaxies, and the properties and the conditions with which stars form in these kinds of galaxies become much more relevant to understanding how star formation happens at higher redshifts. So if we can understand the details of these very nearby galaxies, we can start to understand the physical conditions of star formation at higher redshifts. And so in the local universe, these LERGs are all basically major mergers. Here's just a montage of some of the brightest systems that we observed with our Hubble program. And in general, GOLS consists of the 200 brightest LERGs in the revised Bright Galaxy sample. And the ERS program that I'm talking to you today about includes 4 galaxies, 2 Zwicky 96, NGC 7469, NGC 3256, and VV114. I just want to point out that Thomas Lai, postdoc in goals, is going to be giving a talk about the MRS results for NGC 7469. Thomas Bond is here actually with a poster on the NearCam and MIRI imaging for 7469, and Marina Bianchin is actually also here with a poster on the NearSpec observations for NGC 7469. So lots of 7469 stuff here. And NGC 3256, all of our data, NearCam, MRS, MIRI, and NearSpec should be coming in the next couple of weeks. So we're scheduled between December 16th and the 31st. So lots of new stuff coming from goals soon. Okay, so for VV114, VV114 East, which is the nucleus you see over there in the radio, is completely dust enshrouded. You see, we essentially completely miss it in the UV and optical. And it has a 7 micron to UV flux ratio that is 80 times larger than VV114 West, which is primarily composed of these massive stellar clusters that you see shining brightly in the UV and the optical. This ratio of 80 actually makes VV114 the most extreme such dual galaxy in goals. And it's one of the reasons that we chose to select it as one of the 4 in the ERS program. And you can just see that actually in the infrared, where our former Spitzer observations show that the majority of the emission is coming, almost all of it is coming from this eastern nucleus. So what did we learn about VV114 before JWST? Well, from previous Chandra and NuSTAR observations, we know that the soft X-ray emission, what you see here in orange, actually extends far beyond the central regions of the galaxy. And if you look in the hard X-rays, essentially all of the hard X-ray emission is coming from these 3 knots. One of those knots is VV114 East, one of those knots is the nucleus VV114 West, and then a very massive star-forming region. And again, in 3-color image with Spitzer, you can see the east and west nucleus, but we really lack any significant detail for what the galaxy looks like in the infrared. But I will say that the Chandra observations are consistent with the scenario where this diffuse gas is being driven out by a sort of a large-scale galactic superwind. And so one other thing is that because of the compact and strength of the hard X-ray emission, it has been long thought that VV114 East harbors a deeply buried AGN. Okay, so now here is some new data. On the left-hand side is the HST images, 3-color HST images of the system. And now we get to show this beautiful, amazing NearCam image of VV114. And I just want to highlight that what's really shining brightly here is now essentially all of the dust in the eastern nucleus is gone. We're seeing straight through to the eastern nucleus, which is completely saturated in the NearCam images. And what you actually see shining really, really brightly here is not only these young star-forming regions that are traced in the optical as well, but you also see all of this diffuse emission surrounding these regions and out, of course, into this tail out here. And now when I flip from NearCam to MIRI, you see that MIRI is tracing these very, very bright, compact knots of star formation across the galaxy. But one thing that is shining brightly that is kind of took us by surprise, actually, is the just massive extent of this diffuse emission. So this is actually the F77W, and which means that this is actually mostly diffuse polycyclic aromatic hydrocarbons that have been ejected from the galaxy due to this large-scale wind. And so now, for the first time, we're actually being able to resolve the properties of the diffuse interstellar medium in the mid-infrared in these systems. So now I'm going to walk through a couple of the results that we've gotten out of these images. For the NearCam imaging, this is a paper that we submitted to arXiv a month ago, and it was essentially focusing on identifying dust-buried sources in our F150W, F200W, and F356W NearCam images. And here is my version of the 3-color image, which doesn't do justice to how amazing these systems are, but I thought I did an okay job. So one of the things, again, that you'll notice is that what is really popping out here in the near infrared are these really, really red bright knots. And you find them sort of across the galaxy. And in these insets, what I'm showing, again, on the left-hand side is our HST, previous HST image. And now on the right, we're actually showing some catalog comparisons. So in purple is everything that was identified in previous HST imaging in a signal-to-noise of 3 for all 3 of these bands that you see here. This is the U and the B and the I band with HST. In gray, we're actually identifying, these are regions newly identified with NearCam that we didn't detect at signal-to-noise thresholds in our HST images. And you can see that many of them are actually these, the brightest red regions that surround this diffuse dust that you see really highlighted from the 356W. And it turns out that we identify 374 compact star clusters. And by compact, we essentially mean consistent with the point spread function at F150W. And we actually have to increase our signal-to-noise thresholds for the 200 and the 356. And that's because those images show a lot of highly variable background, spatially varying diffuse emission. And so for this first pass through the catalog to identify the most obvious, brightest dust-buried sources, we wanted to make sure that we could cleanly select bright compact clusters. And so we opted for a slightly larger threshold in these 2 bands, but a much more robust and complete analysis of every single star cluster that we can detect in the near infrared is going to be left for our final galaxy, NGC 3256. And so the takeaway here is that 20%, or roughly 20% of these sources appear to be undetected, at least at 435. And while there is some hints of them at 814W, because we essentially could not detect them in any other optical filters, we had no age or mass information on those star clusters. So the previous HST images sort of give us hints. You can see these kind of red blobs here. They give us hints that these clusters were there, but now we're actually finally being able to understand their properties. And so how we do that is we actually use these color diagrams and we compare the measured near-infrared colors to the SSP models. And so one set of simple stellar population models that I'm showing here is the Yggdrasil models, which include contributions from continuum and nebular lines. And in red, I'm just highlighting a couple age points on the curves. Why these sort of look kind of weird, and maybe not what you're used to seeing for color diagrams in the optical, is that the majority of the power in the near infrared essentially comes from this red supergiant transition. That red supergiants sort of come on in around 5 to 6 million years, and then they dominate the light. And so basically, after this point, you're really unable to use the near infrared to really identify uniquely clusters sort of beyond about 10 million years, because all of the ages sort of bundle up together. And so what we're basically able to find is sources that are well outside of that selection, that are so far essentially above that they are, regardless of their contributions from PAHs or even hot dust in the 356W filter, these sources are certainly unambiguously super red and likely very, very dusty and young based on the model tracks. And so where these gray points in this sort of box to just highlight this region, they all essentially are these super, super red points in the middle of the galaxy. So all of these very compact red sources that we're finding in the overlap region actually are these super young sources. And because of their discovery, we're actually able to triple the number of young sources that we detect in the galaxy. So with MIRI imaging, I just want to quickly go through. Again, I sort of briefly talked about it. We see this massive diffuse component in the 7.7 micron, which is very, very different than the 5.6 micron. So we see that the actual 45% of the total 15 micron light is emitted from these 2 cores that are actually separated by only a couple hundred parsecs. So this eastern nucleus is actually composed of 2 separate cores. And just to highlight that, what we think, and so now is the Spitzer IRS spectroscopy of the entire gold sample. And the way to read this is the 6.2 micron PAH equivalent width being low is indicative of an AGN. And so here is actually where the southwest core of the eastern nucleus lies. It lies right in this area where we see all of these strong AGN and goals. And so previous papers actually speculated that between these two regions, the northeastern core, being the much brighter one in radio emission, actually was the source of the AGN. And as it turns out, based on mid-infrared colors and spectroscopy, which I'm going to have to rush through because I'm out of time, the southwest core is actually the one that harbors the AGN. And we're now able to unambiguously identify these things with JWST. And so we also have Spectra to prove that, but I'm not going to talk about that. And I'll leave my summary up and take any questions you have. Thank you very much.
Are there any questions?
Thanks. Great to see all of this too. Nancy Levinson, Space Telescope. I'll open the opportunity for you to show the spectra that you blew by. I would love to see that.
Thank you very much. I appreciate that.
And please give us the highlights that we should.
Sure, no problem. Thank you. Okay, so this is work led by Jeff Rich. The paper has been submitted and hopefully will appear on arXiv soon. What we've done here is just shown the F77W again, and these individual apertures that Jeff has drawn actually correspond to these different regions here. And so what I wanted to highlight is regions A and C. So region A is the northeast core, and region C is the southwest core. And so A, you see this massive, deep silicate absorption. And if I were to zoom in on the PAH here, it's an incredibly narrow 6.2 micron PAH equivalent width. So we know that not only were previous papers wrong in their assessment that the northeast core harbors the AGN, we actually think the northeast core is actually a deeply embedded star-forming region. It has mid-infrared colors consistent with a star-forming region. It has spectra consistent with a deeply embedded star-forming region. And the southwest is actually where the AGN is. And the only other thing I'd highlight here is that region F is actually a star cluster that we detect in the NearCam imaging, and the equivalent width of the PF alpha line is actually consistent with being a 1 or 2 million year old, about 10 to the 6 stellar cluster. So our NearCam imaging is broadly consistent with what we're actually able to get out of the mid-infrared spectra. Thank you for that. Let me explain some of that. Thanks.
Yes, thank you, Nancy. I didn't realize I was such a scary chair. We have time for maybe one last question. Is there any online? Okay, all right, so.
Hard to tell from this distance. Do you detect any neon 6 line, neon 5, neon 6? So those are markers of AGNs, right? If you're not detecting them, that makes it a little more clear.
Yeah, so we don't detect the line, and it is somewhat odd that we don't detect the coronal lines from the southwest core. There is other examples of Markarian objects where that is the case based on particular geometry. So we think that we can sort of explain that, but the details of that and the detections of the coronal lines is sort of outside of my expertise. But we can talk about it offline if you want.
Maybe these two, the northeast and southwest, both are not AGNs. They could be just very deeply embedded star-forming clusters.
The possibility remains that the southwest could also be very deeply embedded. The PAH ratios and equivalent widths seem to suggest otherwise, but I agree with you that it is still a possibility.
Great, let's thank our speaker again.
Everyone can hear me okay?
Yeah, sounds good. And I'll give you a 2-minute warning.
All right, sounds good.
All right, so our next speaker is Kedar Efatye, who will be talking about, he's correcting from high to rather low to intermediate redshift, spatially resolved Passion Alpha detection in the templates program.
Yeah, sorry, I had to do that after Monday's talks, like just amazing. Before I talk about passion alpha detections, I'll be giving a brief overview about Templates ERS program, which I'm part of and led by Jane and Joaquin. Jane talked on Monday about the telescope performance, but I'll be giving an overview about the ERS program. As you can see over here, we have nearly 60 hours allocated time. We have a good website, Twitter handle, and also mainly important for everybody in this room, the GitHub repo. So all our data reduction tutorials or whatever lessons we learned will be uploaded here as soon as we finalize them. So if you want, you can watch that repo and get updated. So this is our sample, just a full form of templates. It's targeting extremely magnified panchromatic lensed arcs, and they are extended star formation. I didn't come up with it, but it's really useful that the main idea was for these 4 galaxies to be templates for all other future cycles and people to have a template spectra. So we are very heavily focused on spectroscopy. Just to give a brief overview of the types of galaxies that we are looking at. The first 2 are cluster lenses and highly star-forming galaxies. As you can see over here, star formation rates a few to tenths. And those 2 on the right are dusty star-forming galaxies. The red is from ALMA. We didn't see anything with HST. So it's heavily extincted dusty star-forming galaxies. We guessed the AV while proposing about 6. You'll see later the results. But the star formation rate from infrared luminosity is over hundreds, which is corrected for magnification. So after magnification, it goes to thousands, the apparent star formation rate. So these are widely varying types of galaxies, and we hope to learn how star formation varies across these type of galaxies. I'm sure everybody has seen this before, but this is from our proposal. As you can see on the right, this is what we expected to see from James Webb Space Telescope. And as you might have seen on Monday, some of the actual data also looks similar to that. These are all the observations that we proposed for. The depths are shown as color bars. So we were going pretty shallow on the imaging, a few minutes exposures. But for each of the IFUs, we are going more than an hour or hours. And we are doing all background exposures, dedicated background exposures, and leak calibration so everybody can learn what are the best practices to use for IFUs. The main scientific goals that we are trying to address with this program is demonstrating star formation rate indicators in an extinction robust way. So we are targeting H alpha and passion alpha for all our galaxies, and H beta for the less extincted ones, and also PAS for the high redshift ones, which are dusty star-forming galaxies. And we also have IR luminosity for the dusty star-forming galaxies. We have UV slope for the lower redshift galaxies. These are the first images that we got. So you can see over here the BCG. There's some residual striping. This is directly from the mass data products. So first day when we got the images, we made this. But Michael has been working on this, and we now have fully aligned images with all the individual clumps that you see over here. And as you can see, this left is, I have to say, NearCam imaging. Right is MIRI. The reddest filter is 15 microns. You can see this particular red clump. That's also visible at 21 microns. So that's really exciting. And Michael is working to do resolved SED fitting for all these clumps. Another exciting result, passion alpha at redshift 1.3. So I have to play this from here. I'm going to step through the different slices. You can see it is crazy bright. I'll change the color scale here in a bit to show the star-forming clumps. So this was so bright that the pipeline thought the bright clumps were outliers and flagged it off. So Brian has been working a lot with dealing with the pipeline and getting us really good IFU cubes. And that's the spectra that you see of this particular passion alpha. We also have lots of other lines at different grading setting. And he'll be working on paper, and Justin will be talking about that in the talk after this as well. So I'll be switching gears to dusty star-forming galaxies, the two other targets that we were seeing in the proposal. So just to give a background, this is a recent blind survey from ALMA. They claim that the dusty star-forming galaxies would dominate star formation in the past 12 billion years. You might have been used to seeing this type of plot from Madar and Dickinson, 2014. This is type of an update on that, which shows that dusty star-forming galaxies contribute heavily. So understanding what's going on in these type of galaxies will help you understand how the universe works, since the large-scale simulations such as Illustris TNG fail to produce the number counts that we see in dusty star-forming galaxies. That's by about an order of magnitude. So there's a lot of things to be learned by studying dusty star-forming galaxies. The two galaxies that you saw was selected from SPT-SMG sample. This is a spectroscopically complete sample, ranging from 1.9 to 6.9, and the two galaxies are 3.7 and 4.2 redshift. So before James Webb Space Telescope, what did we have? We had HST data. As you can see, the contours are from ALMA continuum data. We didn't really detect anything in HST after galactic subtraction. And IRAC is a big PSF, so we don't know what is real in that or not. But these are basically galaxy-galaxy lenses. So there's a foreground galaxy and a background galaxy that's being stretched out. So it stretches out over here, and we don't see anything. So this is what we get from NIRCam and MIRI. Again, a place to pause and thank everybody involved with this telescope building and maintaining and operating. This is really amazing. While proposing, we didn't expect anything like this. And as the previous speaker said, it's very popular in general public. You might have seen these floating around on Reddit, and they did make really beautiful color stretches. I can't achieve that with Apple Pie, sorry, but this is pretty close. And as just to see, like, these details are amazing, and also the ring over here. You can see the clumps over here getting brighter and brighter at mid-infrared wavelengths. Those are, like, we are thinking very embedded star-forming clumps. Just to show that in grayscale, which, like, DS9, first look, okay, amazing. This is 3.5 to 21 microns for SPTO for 1847. And next is this. So we use WebPSF to subtract the lens from the data, and this is just NIRCam long wavelength imaging. Blue is 2.7 microns, green is 3.5, and red is 4.4. So this work has been led by Jared Cathy at University of Florida. He dealt with the 1/f striping, and then Galfit subtraction been done with Anthony. And he's been really into the weeds with modeling this lens. So this is what you get, after doing source plane modeling. So what we think is there's a foreground lens caustic over here, and it stretches out like this. And the blue clump over there is actually a merging galaxy right over here. And you see some tidal trails. So that's really amazing. It's a paper in prep. It will be out in a few weeks. Be sure to look out on arXiv. Moving on to Passion Alpha, which is where I'm focusing my energy into. So just to introduce Passion Alpha, since not many people think to look at it. As you go into very high extincted dusty sources or dusty star-forming clusters, Passion Alpha actually gets brighter at extension of 12. So if you want to really study deeply embedded star-forming regions, it's better to look at Passion Alpha rather than H alpha or H beta. And it's a better indicator of star formation rate going on, since we have a smaller correction to do with respect to extinction. And this has been really difficult since from the ground it makes it really impossible to observe at that wavelength. We had Spitzer, and there is one data point at redshift 2.5, which was unresolved. So this is the highest redshift Passion Alpha detection. that I know of, unless somebody else comes up later and gives a redshift 10. So I don't know. But this is really amazing. It's spatially resolved. Thank you. And you can see different regions getting brighter in Passion Alpha. On right is a masked image from ALMA dust continuum. So that's where the dust dominates. So you expect the extinction to be more in those regions. As I've overlaid Passion Alpha contours on there, you can see some of the emission overlaps, while some is slightly offset. And if you do, I'll show it in the next slide, but that's really interesting to see the variation in extinction going on and where the emission is coming out of. So there's a lot of stuff going on, and we probably need source plane modeling to actually understand what's happening in the source. That's a spectra. That's line continuum subtracted, and I've just overlaid C+, which is another star formation rate indicator from ALMA, and the line width matches pretty well. And just to show how it looks across the different slices. So I'm going through the yellow region, and you'll see different regions of rings popping up at different wavelengths. That's a little bit of velocity information that you get from the cubes, and advantage of having IFU spectroscopy. And that's the spatially resolved results. So here I'm just dividing Passion Alpha luminosity with IR luminosity that we have from ALMA, and correcting for integrated extinction. So as you can see, there's lots of variation going on over here that we think is from extinction, and also from different star formation going on at different extinction levels. This is basically to show how IR luminous this galaxy is. These are all local lugs and ULUGs, which I now have to update given the recent talks and all the recent JWST data coming out. But nothing has been shown about redshift 0.5-ish, except for this point, which is at 2.5, and this was unresolved with Spitzer. And now we have at redshift 4.2 very high IR luminosity, and these are all Paxels resolved points over here. So we can generate a IR luminosity versus Passion Alpha curve on this one. So that's where I'm going to leave at. This is still in prep. I've inflated the errors because we are not sure about the absolute calibration and how much of an error comes from correcting for extinction from H alpha flux. So that's still work in progress, and looking forward to the NearSpec reference files. And thank you for your attention. This was our collaboration meeting last August. Lots of people missing, but there was, since it was hybrid mode, but it's been a great time working with all of them, and I've been having a lot of fun last few months. I'll take questions. And
Thank you. There were lots of questions.
Yeah, sure.
Great results, thank you.
Thank you.
So could you go back to where you had the Passion Alpha? Yeah, this one. So you said the green points are not corrected for magnification, right?
Yes, they are not.
And by how much would I have to shift those points down, more or less? Do you remember how much?
So these are individually resolved, so we don't have individual magnification results yet, since we just finished the continuum lens modeling. So this integrated one has been corrected for magnification. That's about factor of 32. So since it's nearly an Einstein ring, it's a large magnification. So we'll be working on that, but I don't have any results to tell you right now.
You're all nestled in the back, so.
Thank you for the very nice talk. I'm from University of Arizona. So I want to like to know if you detect any other lines in the data cube. I'm especially interested in the iron 2 at 1.646 micron.
Iron 2?
Iron 2, yes.
Okay. I don't think so. We detect that, at least looking from the cubes. But we tried Passion Beta. There is, I don't want to claim anything, but yeah, there's slightly a hint of maybe, but I won't claim it as a line. So we'll have upper limits for Passion Beta and bracket alpha. So to constrain the extinction more. But yeah, no more detections in the NearInfrared, except for Justin's.
Susan, are there any questions online? All right, if not, we'll thank our speaker.
Thank you.
All right, sound okay? Good? I can sort of hear it, so I'm going to assume that's a good.
All right, so we'll be rounding out the session with our next speaker, Justin Spilker, who is also working on the templates program, looking at the smallest dust grains in the early universe, smoke rings and the Earth.
That's right. Thank you so much for the chance to be here to speak. In particular, on behalf of the Templates collaboration, Kedar did a great job giving an overview of our ERS program, and I'm going to continue the theme a little bit. And in particular, we're going to talk about that exact same galaxy. So this is 2 talks on the same galaxy. So to the SOC members in the room, thank you. I'm going to interpret this as saying that this galaxy is roughly 20% as important as the Milky Way, just based on the ratio of number of talks. And so I won't go into a lot of overview about the program in general, since Kedar did a great job of doing this. Again, the idea is basically that we're going to try to assemble all of the most commonly used indicators of star formation at high redshift and compare them all to each other. There is a true number for however fast these galaxies are forming stars. And so the question we are trying to answer is basically, do the numbers that we get from different tracers agree with each other, and where and how? In the regions where they don't agree with each other, why might that be? And so I'm very happy to share a few preliminary results from some of our junior folks. Working with these IFU data products has not been easy at all. Anybody who's just like downloaded the default reduction from MASS has probably seen that these data are quite challenging. And so I wanted to highlight in particular one piece of upcoming work from Taylor Hutchison, who's a postdoc at Goddard with Jane, who's now made these very nice maps of the rest optical nebular lines in one of the UV selected targets here. And you can actually just sort of see by eye, which I think is really cool, these variations in the ionization. So this is a map of the O3 to H beta in the optical, and you can actually just see these regions where O3 is high in comparison to H beta, just visibly, and I think that's really amazing. One other early result that's upcoming from a postdoc of mine at Texas A&M, his name is Jack Birkin. This is looking at those rest optical nebula lines in those very obscured sources. And so these were observations that were just simply not possible before Webb. These lines obviously were redshifted outside of atmospheric windows, and the extinction, as Kedar mentioned, is 5 plus. And so these sorts of observations were very, very difficult. And so what he finds is that by making these maps of the resolved N2 to H alpha maps, we know this isn't the best metallicity indicator in the world, but it seems like these 2 galaxies, even though they're forming stars at a rate of 1,000, seem to be very consistent with the sort of relationship that you expect between mass, metallicity, and star formation rate for galaxies. So I promised to talk about small dust grains, and so I shamelessly swiped this plot from Thomas Lai to just sort of illustrate the spectrum of PEH features that we're looking at. And so for the very highest redshifts, by the time you get to about redshift 3 and 4, the only diagnostic that will be available to us in terms of PA features is this line sitting down here at 3.3 microns. And this line was almost basically completely ignored by Spitzer studies because, as you can see, it's like a factor of 10 fainter than these much brighter features. And so we have some good samples these days from the Akari satellite for low redshift sources, but there's a huge window of discovery space to learn about these very small dust grains at the high redshift universe. So this feature in particular is the shortest wavelength PA feature, so it's the one that you can get to the highest redshifts. It also arises from the very smallest PAs. These are the things that have, quote unquote, only 50 carbon atoms on them. And so, so there's a lot of room here to sort of learn about PAs at early times. And so this was basically the summary of where we stood in the pre-Webb days. These are the only 5 detections of this feature at high redshift. They go out to about redshift 3 here. And the previous highest redshift detection of a PA feature was the result of a heroic 24-hour on-source with Spitzer observation of a galaxy at about redshift 4. That was work that was heroically championed by Alex Pope and Lee Armis. And the results that I'm going to show you today are after an exposure time of 1 hour. So this is really just sort of to illustrate the advances that Webb has allowed us to make. So just as an aside, as far as I'm aware, the stuff that I'm talking about now is going to be the faintest thing that people have been trying to look at with the MRS. Certainly that's true compared to the talks that we've been seeing so far today. And so I wanted to talk a little bit about one particular way that we've pushed the depth to basically reach the maximum possible that we can from the MRS. We're at the regime where these cosmic ray shower artifacts are the primary limiting factor in our analysis. And they basically show up in your cube as horizontal stripes. The reason for that is basically due to the way that the 2D frames map into the 3D cube. And so that's sort of illustrated here where you have the wavelength direction going along this way. Each of these individual slices get mapped into the Y direction of the cube. And the X direction of the cube comes from basically going across each of these slices horizontally. And so if you imagine you have some shower artifact, they're these big blobby structures, they basically black out all of the X pixels in a given Y slice. They're coherent over tens of channels in wavelength, but they don't impact that many Y pixels in height. And so what that means is that you wind up with these artifacts that look like horizontal stripes. And so I did a lot of effort to basically develop a template to remove these stripes, and this is just sort of to illustrate that. The pipeline these days has some sort of first-order attempts to correct for these artifacts, but when you're trying to push to the faintness of the features that we're looking for, even that is not enough. And so I developed this technique to basically make templates of these stripe features and remove them. And so I'm happy to talk about that more with folks if you are also considering pushing to preposterously deep depths with the MRS. And so, yeah, there we go. And so here's our spectrum of the PAH feature. This is the highest redshift detection of a PAH thus far. And again, it only took less than an hour on source. And so you see very clearly we detected that redshifted 3.3 micron feature. The purple line is just a smooth spectrum because the intrinsic spectral resolution is too high for us. Question mark aliphatic feature off there to the right. That one is much more tentative. So I'm not really going to talk about that, but maybe with improved data processing, we'll know more. And so the great thing about the MRS is that it works as an IFU, and so we also have spatial information. And so just to orient you, this is an image of the continuum that I've collapsed from within the cube at about 3 microns. So you're again seeing that beautiful Einstein ring of the lensed galaxy in the background. At the center there, that's basically 3 micron emission coming from the foreground lens. And so that will not show up in the subsequent panels because that only exists in the foreground. And so here's our PAH map. You can see that it looks actually pretty different compared to the distribution of flux that we see in the continuum. We see these 4 bright knots of emission, which is kind of what you expect given the lensing configuration, but they're not at the same positions. We see a different distribution of the flux between the PAH and the continuum emission. And that's also true for the longer wavelength emission that we observe with ALMA. This is the emission that's arising from the much larger dust grains. And so it seems like we have these very clear offsets between the smallest dust grain emission and the largest dust grain emission. And we're still trying to understand exactly what that means. And so if you have thoughts, there are definitely people in this room who know more about PAS than I do. I would love to hear thoughts. And so one of the results of this is that the equivalent width of the PAH feature is strongly variable across the source. And this has previously been suggested as a way that one might detect and characterize obscured AGN activity. And even in this resolved map, we actually don't find even individual pixels that fall below those kind of threshold values for an obscured AGN. And so it seems like this galaxy probably really legitimately is dominated by a starburst, dust-obscured star formation without an AGN. Similarly, if you compare the emission of the PAS to those larger dust grains at the far infrared wavelengths, we find, again, these factor of 10 variations in the ratio of those 2 luminosities. And so what that tells you is that this is not going to be an easy magic bullet star formation rate indicator. I think as a high redshift person, or low redshift now, whatever, we often have this tendency to say that, the next data is going to be the magic bullet that solves all our problems. And we definitely did that in this proposal, I cop to that. And it looks like, again, this is not going to be just a very simple indicator of the star formation. But these PA features are the only spectroscopic signatures we have available to us to diagnose the dust. And so it behooves us, I think, to really try to understand what it is that we're actually seeing here. And so with that, I will wrap up. I think it's really an exciting time to be starting to understand these PA features because Webb has really allowed us to enter this new regime where these kinds of observations that were just completely out of the question with Spitzer are now going to be basically trivial. This isn't the highest redshift source that we have in the sample. It's not even the highest redshift source that anybody that one could do this with, obviously. It's just one that we picked because we liked it, to be honest. And so there's, I think a lot of room to push the redshift frontier for, spectroscopic conformations of dust as well. So I'll leave it there and take questions. Thank you.
All right, good. We have lots of time for questions.
What about small grain population? You show the PA, 17 micron. If you do 17 to 25, I don't know how far really have sensitivity, but maybe you may be able to start to see small grain population of continuum. This is the only PA feature that we can cover. So this is the only one that we'll actually have. We also don't have the full wavelength coverage of the MRS because we only cared about the particular lines that we were interested in. And so this is basically the bandwidth that we have around this PA feature. So I don't have a lot to say about possible small grain populations. The comparison that we're really going to be able to make is between this feature and the much longer wavelengths that we see in the far IR. I would love to be able to get the other PA features, but Webb cuts off. We'll need a future far IR observatory as well.
Any questions online? Susan, you go ahead.
I do. Christina Borsma says, any insight on how much of the IR emission is carried here by PAs?
Well, so in this single PA feature, it's some tiny fraction. It's like 10 to the minus 3 of the total IR luminosity is in this feature alone. And PAs, if you had the whole spectrum, would be, an order of magnitude, a couple orders of magnitude higher than that, so 10%-ish.
You overlay the PA map against ALMA C2?
Yeah, so we have done that. They all look different. This was kind of like the biggest surprise to me because I kind of expected that most of these tracers would, match each other, and they just really haven't. And I'm still trying to wrap my head around what exactly that means.
No, but from this map, it looks like 0.3 does overlap with a 660 micron continuum. Is C2 probably will trace a little bit better, right? Or you don't see the
possibly, yeah. I think a lot of the overlap that you're talking about is basically just because the lensing geometry forces all wavelengths to look like this ring, right? So the thing that I think is interesting about this is that like the far IR peaks here. That's this region here, which is not bright in the continuum. And that's this region here, which is close to but offset from the brightest regions of PA emission.
I think it might be easier if you do a racial map.
Yeah, I'm happy to, I can talk more about that with you offline, sure.
All right, so conscious that it's lunchtime, we're going to wrap it up there. We're going to continue with Assembly of Galaxies after lunch at 1 p.m. Eastern. Are there any announcements, Susan?
Only there are a couple questions from previous speakers that so you might go look at the Slack channel and answer them if you were a speaker in this session.
All right, and so let's thank all our speakers. Thank you, that was great.
There was only one button and I was afraid to push it because I didn't know what it did.
It looks like it's not an on or off kind of button, I agree.
Yeah, maybe we used to.